Hi, welcome back to Physical Chemistry. My name is Kevin Tokoph. Make sure to like the video and subscribe to the channel for future videos and notifications. So in the last video we did a lot of transformations of derivatives, integrals, differentials, and all sorts of stuff with Newton's laws. We're now going to do this with Coulomb's laws because in general Coulomb's laws are a lot more applicable to physical chemistry directly, because when we get into quantum mechanics and we start dealing with Schrodinger's equation and how it relates to a hydrogen atom, multi-electron atoms, we're going to start using a lot of Coulombic equations and variables to help us understand exactly how the atom is set up and so forth. Okay, but that's a long time from now. But the main thing I want to do here is get you accustomed, again, to the same thing we were doing before, how to take one equation and transform the derivatives, transform the differentials to get other things that are useful. Okay? So here I'm starting with Coulomb's law. This is the force due to one charge on another charge. This is the force is equal to Coulomb's constant, which is approximately 9 times 10 to the 9th Newton meter squared per Coulomb squared, times Q1 times Q2, the two charges, divided by the square of the distance between the charges. All right, so K, Q1, Q2 over R squared. The first thing I'd like to do is actually multiply both sides by dr. Okay? Why am I choosing to do that? Well, whenever I'm dealing with electrostatics, in a lot of cases, sometimes when you have really simple problems, you tend to deal with Cartesian coordinates. Okay, so x, y, and z, right? When you're dealing with electrostatics, because in most cases you're really ultimately doing things on the atomic level, atoms are spheres, right? So I would much rather deal with polar coordinates, or to be specific in three-dimensional spherical coordinates, to do that. So normally when you saw, and this is just kind of a side note, whenever you, when you saw that work was equal to the integral of force times dx, and it's really force dot dx because it's the dot product. For when you're dealing with polar coordinates, you can also write work is equal to integral of f dot dr. Because when you're dealing with spherical coordinates, which is polar coordinates also, you're talking about a radius, a distance from the center, which is normally the charge of interest, to a particular point, but that's going from the point in the center of a sphere to some point away from the center, so that's radius. So when I have this f dot dr, that's just work. You can sort of think of the dr as the same way as dx. But that's the point. I can multiply both sides here by dr. Okay, I can do that. And what I'm then going to do is I'm going to integrate both sides. Okay, so work is going to be here the integral of dw, which is the integral of k q1 q2 over r squared dr. Also, remember from the previous video, and we showed it in that video, but work is the change in kinetic energy. So it's the integral of d kinetic energy. But there's another thing that comes from conservation of energy, not something you normally do with this method, but the change in kinetic energy is the negative change in potential energy. So we can actually relate everything this way. All right, so I can say that the change in kinetic energy, or the work, is equal to the integral of kq1 q2 over r squared times dr. Well, I'm just actually going to integrate this from r1 to r2, and in general, because r1 is the center of the atom, r1 is 0. Okay, in some cases it might not be. You might be looking at other charges, but if you're looking at, say, the nucleus, r1 is 0. All right. So what do you get when you do this? Well, if r1 is 0, when you evaluate this, you actually get that the integral here is negative k q1 times q2 over r. This expression right here, okay, this is the change in kinetic energy, all right? Assuming you go from r1 is 0 to r2, okay? Another way, this right here, this integral, oops, let me actually redo that. This integral right here from r1 to r2 of k q1 q2 over r squared times dr, this is the integral form of the change in kinetic energy for a charged particle, okay? So if you measure the distance between two charged particles and one of them is moving, this is the kinetic energy of that particle. It's also the negative change in potential energy, right? All right. So hopefully that makes sense. That's how you can multiply both sides by dr and get the kinetic energy of a charged particle when it's in the electric field of another particle. All right. One other thing that is really important also is that force divided by one of the charges is the electric field of the other charge. In other words, if I were to take this expression right here, which is Coulomb's law, and divide by Q2, I'd get force over Q2, but that would leave KQ1 over R squared. This right here is the electric field of charge 1. All right? Now, what I can do is, there's another relationship that is a lot more difficult to show, but it's basically that the derivative of voltage with respect to radius, this is not resistance, this is the derivative of voltage with radius, is the negative of the electric field. So what can I do to calculate the voltage? Well, I'm just going to multiply both sides by dr. Right? So I'm going to cancel this dr, so I get that integral of dV, which is the voltage or potential, is equal to negative integral of electric field dot dr. I can take the expression for electric field, KQ1 over R squared dr, and what do I get when I do that? Well, when I actually evaluate this integral, it's actually going to be KQ1 over R. What is this? This is the voltage. This is the voltage. KQ1 over R, the radius, is the voltage. Now, what do you notice from over here? What did we say the change in kinetic energy was? Or really, I'll say the potential energy. The potential energy is actually KQ1, Q2 over R, right? Because if this had a negative sign, remember a negative sign, kinetic energy, change in kinetic energy would be negative KQ1, Q2 over R, right? That comes out of this. But if you take the negative sign away, it becomes change in potential energy. But what do you notice? This voltage is the same thing as the potential energy minus Q2, right? So what that means is if I were to divide the potential energy by Q2, that would be KQ1 over R, which is the voltage or the potential, right? So that's another relationship that we have. If you want to find the voltage, you take the potential energy and divide by the other charge. Which also means that because delta U is the negative of the change in kinetic energy, that the potential energy over Q2 is the negative of the change in kinetic energy over Q2. Okay? Also, another thing that we can also show that may not be as useful, but it's also worth showing. If you have have a situation, let's suppose I had some particle right here. Let's say it's a positive charge. Let's say that it's fixed. It doesn't move. So it has a velocity of 0. It's fixed. Let's say I have another particle, maybe another positive charge, and this one is going to move in that direction, right? So this one's fixed. This one actually has some velocity. Okay, we don't know what the velocity is, but this one's fixed. The force, electrostatic force, is just KQ1, Q2 over R squared. Now, by Newton's second law, it still applies that the force is also equal to the mass times the acceleration, right? So, if you were to say know what charge 1 was or charge 2, and you actually knew the distance between them, which in this case this would be R, you know K, it's Coulomb's constant, you can actually calculate how fast the particle will be moving, or in other words, how much it accelerates, right? So how would you do that? Well, if we know that MA, which is the force, is equal to, this is electric field times Q2, we can also write that as KQ1, Q2 over R squared. If you wanted to find the acceleration of the charged particle, let's say this is acceleration, this is particle 1, this is 2, so the acceleration of particle 2 is equal to KQ1, Q2 over R squared times 1 over the mass. In this case, it's the mass of particle 2 because particle 2 is the one that's moving, okay? So if you knew the mass of 2, if it was an electron, this is a positive charge, but if it was an electron, you would just take the mass of an electron, whatever that is, I don't honestly remember what it is off the top of my head, and just plug that in here. You take the radius between them at a given point, and then K, Q1, Q2 are also known. Now, One thing I'll just mention because it's worth mentioning now, just because we're on this topic, this acceleration and all this information right here, this is at one point in time. Okay, this is one point in time. Why does it have to be at one point in time? You're measuring the an instantaneous acceleration at this point. What's the acceleration right there? Okay, because the acceleration is going to change because r is changing, right? R is changing. This particle gets farther and farther away, right? So r is getting larger and larger, so the acceleration will get lower and lower. So you have to put it at one snapshot, one point in time, and then look at the acceleration at that time, and you'll find the acceleration decays as it gets farther and farther away, okay? But that's beside the point. Hopefully you can see now that you can essentially take Coulomb's law and Newton's second law, basically, multiply by differentials, take some appropriate derivatives and integrals, and you can end up with most of the electrostatic equations. And again, this really doesn't directly relate to what you're doing in physical chemistry right now, but just seeing how you can manipulate derivatives, integrals, differentials, hopefully you will get some practice, because in chapter 3 at least of the book that's used at this school, you're going to do a lot of that. And if you're having trouble with that, you're going to have a lot of problems in the rest of PChem 1 and PChem 2. So get some good practice with this now and save yourself the trouble later. Thanks for watching the video. Hope it helped, and see you in the next video.